Okay, good afternoon everyone and welcome back to the session after lunch and welcome to the third and final Infosys-Chandrasekhar lecture by Professor Joel Moore. And today he's going to tell us about quantum information and other tools for understanding dynamical regimes far from thermalization.
Thank you very much. And I get to build on earlier talks in the meeting, and especially the one by Masaki this morning gave a nice explanation of one fact I will use a couple of times. Maybe a better title for the talk is what entanglement has been good for in condensed matter and how that's evolving, because we're supposed to be in the age of quantum information, if you go by the subtitle. So what has been going on in that age? So there'll be a bit of a long introduction. The stuff I want to build up to is that entanglement has turned out to be a very useful probe to understand some things about thermalization and non-thermalization. And then more recently, I have discussions of experiment at the end, even though the beginning is fairly theoretical. So at the end, I will have a little interlude where I talk about the new spin liquids that I didn't quite get to last time. But the main story to kind of wrap up the meeting, or my part of the meeting, is maybe the first measurement of a many-body entanglement quantity in the solid state, not counting cases where you engineer qubits or something using solids. So I mean kind of natively in a simple material. And that actually is a fairly short calculation. So I'm probably going to spend more time on the introduction than on the end. But one sort of recurring theme is to try to look for aspects of entanglement that are a little bit universal, and that lets you narrow down which of the many different entanglement quantities you might look at, and then ask, it turns out to be useful, especially for dynamics, as a probe of when interacting theories are different from free ones, or how are they fundamentally different. All right, so let me go ahead and start, and this will be quick for this crowd. Simplest case of an entangled state might be the singlet, where well-defined state of two spins, a pure state of two spins, but if I only look at one spin, then I have to think about a mixed state. I've created some entropy by only looking at one bit. So the operation is trace over subsystem B, get a density matrix for subsystem A, and magically we've gone from a pure quantum state to some kind of classical entropy. And that idea goes back quite a long way. So the entropy I'm going to be talking about for several points, it's not my only entanglement measure, but it will be the one I use the most, is this von Neumann entropy of the reduced density matrix for one subsystem of a bipartite system. And if I count it in bits, then this is log base 2. So that quantity turns out to be surprisingly useful for various things. And maybe two quick comments. I mean, it might not be totally obvious, but you can work out for yourself that it's symmetric between A and B, assuming that I started with a pure state. Even if, say, subsystem A is a lot smaller than subsystem B, that gives you a clue to, in a local theory, what might determine the von Neumann entropy. And the second fact is this reduced density matrix for subsystem A is a very natural and important object, because every observable you could measure that is only supported on subsystem A will be determined by that partial density matrix. All right, so maybe the simplest way to view entanglement entropy would be in states that are just a whole bunch of singlets. And there are various cases of this. In fact, the two examples I'm going to do of where entanglement entropy taught us something about a state maybe that we didn't know, or at least can be calculated in a fairly universal way, you could both understand a little bit in this sort of singlet or dimer picture. So what I mean is I might have states of spin halves where somehow the state breaks up into a bunch of pairs, and then if I'm counting the entanglement entropy in one of these states, I just need to count the number of singlets that cross the boundary between subsystem A and B. So I'll come back in a moment later on to why that might be a physical kind of state. But first, let's just make some simple guesses about how entanglement might behave if we focus on ground states of local Hamiltonians. And let me spend 15 minutes or so with two examples of that, where the behavior is not that hard to calculate, but surprisingly interesting. So if we think about partitioning a very large system into a finite subregion and an infinite complement, how might we expect the entanglement entropy to scale with the linear size of the subsystem? So in a kind of short-ranged state where we could ignore the entanglement between any points that are more than some distance psi apart, then we would expect that entanglement entropy is determined by some shell of thickness psi around the boundary. This makes sense because the boundary is the simplest property maybe that A and B share, and that leads to something called the area law, which is not really a law in the sense of always being true, but it's maybe the most natural thing to happen in local theories, and it is close to a law in some cases. If you have a gap in one dimension, for example, it's certainly a law. Anyway, so that would be some scaling like this, L to the d minus 1. So not as the volume of the subsystem, but the area. If we didn't have any notion of locality, then we might get a volume law. And indeed, if we want to produce an extensive entropy out of entanglement, then we would need to have volume law, and that winds up being important for, say, thermal states and the entanglement eigenstate thermalization hypothesis. So a violation of the area law, one of them is the one that Misaki introduced, which is this famous result of Holgi et al. And then Calabresi and Cardi saying that if we look at a quantum critical point in 1D described by a conformal field theory, which is many but not all of the interesting 1D quantum critical points, then the entanglement between some finite region of size L and the rest of the system goes like log L, while the area law would just be a constant, and the coefficient in front is some number 1/3 times the central charge of the CFT, maybe the most important single number to characterize the field theory that describes this critical point. And if we move away from criticality, then as you might guess, this L gets cut off by the correlation length of the system, essentially. So there's very universal behavior for that kind of quantum critical point. Trying to find similar universal behavior for other but still tractable quantum critical points is the other thing I want to say with two examples. So just to kind of summarize other old calculations in the early days of entanglement entropy in many-body physics, another violation of the area law is free fermions in any dimension. We know that free fermions with the Fermi surface have a lot of low energy density of states. They have a high specific heat and so on. And that shows up in the entanglement. You get L to the d minus 1 times log L, and the coefficient that I didn't write is basically the Fermi surface area. And then there's a kind of subleading correction to the area law, which is hard, I think, to measure in any experiment, but good for numerical experiments. If you took topologically ordered phases in 2D, there's a very beautiful correction worked out by these two groups of people at the same time, the so-called topological entanglement entropy. And that gives you a way to detect topological order without having to put your system on a torus or something like that. You basically just cut your A and B partitions a few different ways and kind of add and subtract them, and you get something that tells you about the topological order in the theory. And then there are some results in higher dimensions, but they tend not to be very complete about the geometry, I'll put it that way. But there is one case in higher dimensions where we can do something very explicit, and it's actually to use conformal field theory in a slightly different way. So what I want to do as a model calculation of a higher dimensional quantum critical entropy is to work on a somewhat special class of wave functions that actually appear at the critical point of quantum dimer models in some other places. They're usually called Roxar-Kivelson wave functions. A more general name is Eduardo Fradkin loves this name, and he was the co-author, but conformal quantum critical point does not mean a quantum critical point with conformal invariance in the standard sense. That would have z equal to 1. There's a class of problems where effectively the quantum wave function is a sum over configurations with a weight that is given by some 2D conformal field theory, that is 2 plus 0D, effectively classical. So these are a strange set of quantum wave functions, but they turn out to appear in various physical problems. And since we know so much about CFTs, it's natural to ask, what does the entanglement behave like in these states? And I'll take you through that quickly because it has a replica trick that is no harder and maybe even simpler than the Holgi one that you heard about earlier. And it leads you to a nice version of the area law. You get area law plus a piece which is the central charge of the CFT that appears there times a logarithm of the energy of the length scale, and then some extra piece. So let me try to give you a picture of where this comes from. So again, it's a bit like the topological entanglement entropy in that the more universal quantity is in the sublinial piece. And just like there, the first term is non-universal in the sense that beta depends on lattice regularization and things like that. Here, alpha is actually going to be a kind of topological number. So the second term is universal, but the first term is not. So where this is going in just a couple of slides, let me kind of roadmap the calculation. Basically, the universal part of the von Neumann entropy of a wave function like that under a partition into A and B is going to be determined by the free energy of the conformal field theory that I used to construct the wave function. And it turns out to be related to a standard problem in sort of geometrical aspects of conformal field theory. And as with many such problems, John Carty was one of the key people in answering it. If you take the free energy for A and B and then subtract with sort of Dirichlet boundary conditions at the boundary between A and B, and then subtract the free energy of the whole system without the boundary, you get a very universal result that turns out to control a big piece of the entanglement. And just like before, in many of these entanglement calculations, you use this replica approach. It's much more controlled than the replica trick for, say, disordered systems and things like that. Anyway, we can write this as a nice ratio where we'd like to understand, as n goes to 1, in a sense, what is the trace of rho to the n divided by trace of rho quantity to the n. And that, I'm going to go through a little bit quickly, but it leads you to a problem about kind of stitching together n copies of the system in a certain way. And basically, the numerator and the denominator wind up looking different in an interesting way. And the part that I can justify for free fields maybe quickly, but not for general theories, it's sort of a conjecture for general theories still, I would say, is that every replica on A is stitched to two different replicas on B by the way that the trace of rho to the n works. If you sort of wrote that out, rho to the n, and put in resolutions of the identity, this is the example for two replicas basically, but this is kind of showing how going from replica 1 to replica 2 on the A side winds up with both of them coupling to one replica on the other side. So this is the kind of stitching of replicas that appears in this problem. In the denominator, it's much easier. We just pair the same replica on A to that replica on B, so it's kind of like just horizontal lines. And now we get the problem that reduces to actually an even older than Carty and Peschel kind of problem. Mark Katz, I guess, is the one that I know of who worked on this a long time ago. The basic idea is then somehow this trace of n replicas appearing in the calculation becomes a ratio of CFT partition functions where the top one is n configurations of the fields, but where all the configurations are stitched together and agree on the boundary between A and B over n independent configurations. And then the replica limit of that turns those partition functions into free energies. So as an example of how this is going to work, if I took free fields, I would have n configurations that agree on the boundary, but I could sort of rotate my variables of the n free bosons and get one free field, and then all the others are Dirichlet because they're stitched to that one free field. And then this problem of free energies with different boundary conditions and CFTs, that is an old problem sometimes called hearing the shape of a drum. And we're doing an easy case, which is a 2D connected region with smooth boundary. In other words, hearing the shape of the drum was about the spectrum of the Laplacian, or basically a drum that is got some complicated shape, and whether the spectrum uniquely determines the shape of the drum. We're not going to worry about that uniqueness question. We're just going to worry about what do people know about the spectrum of field theories with boundary conditions of enforcing Dirichlet on some shape. And the answer, and there's some beautiful old lecture notes by Mark Katz on this problem, is that there are pieces that are kind of non-universal, but that are the leading behaviors you'd expect. There's a free energy that goes like area of a piece of the drum. That will cancel out between the separated pieces and the unified piece. There's a piece that goes like the length of the boundary. That will give us our entanglement area law. But then the most interesting piece in the thermodynamic limit of the shape of a drum is something that involves, for a general CFT, this is what Carty and Peschel did, central charge divided by 6 times the Euler characteristic of the drum head times the logarithm, where Euler characteristic is 2 minus twice the number of holes minus the number of boundaries. So the most important topological fact about 2 manifolds. And there are additional logarithmic contributions whenever the boundary has a sharp corner. So this is kind of the result for a smooth boundary. So now I'm not going to go through a lot of computational details. I will show you one later numerical check. But basically now we can put everything together and get boundary terms and log terms. And now, this combination of Euler characteristics, well, one reason why people care about the Euler characteristic is that it's a nice topological invariant. In particular, if A is enclosed in B or B is enclosed by A, this will actually be 0 for smooth boundaries. If I had a boundary with corners, that won't be true. Or I could have a situation where A and B, one of them doesn't enclose the other. So just some little pictures about how this formula works out. Here are cases of logarithmic entanglement entropies for conformal quantum critical points and different ways of cutting. So here it's 0 because B encloses A. Here you get a minus C over 4 because there's no enclosing relation. I've just cut the system in 2. And an example of corner contributions, if I took a square boundary, I will get minus C over 9. That's how the corner contributions work out. So with a little bit of fun math, you can compute the log contribution. And I won't say more about it, except that we couldn't figure out a way to check it at the time, but a few years later, a student of mine who's now faculty at Berkeley, Mike Zalatel, figured out a numerical check, and indeed you get exactly the log contribution that you're supposed to by doing DMRG numerics actually on the XXZ model, very similar to things we've heard about in this conference. So that's my first example of where you could calculate entanglement and see something about the geometry dependence. The second, I think, was maybe more useful for answering condensed matter type questions. So there's an approach that I will introduce you to very briefly for random quantum critical points in one dimension. So random critical points in general are very hard, and in higher dimensions we have very few results, and as you know, the spin glass is a famously hard problem. It's such a hard problem you could say that Parisi got a Nobel Prize not exactly for solving it, but for having a lot of insights about it. I still wouldn't regard it as totally a solved problem in higher dimensions, but in 1D, there's a very simple approach using just ordinary perturbation theory, and you can actually use that approach to calculate the entanglement. And for these random quantum critical points, so for example, if I just took a Heisenberg spin chain, antiferromagnet, and I ask about the ground state, and I have some spatially varying couplings, that winds up being a very different problem from the uniform Heisenberg chain that was the hero of the last talk. It has, instead of z equal to 1, like conformal scaling, it has z equal to infinity. It is sort of random critical, and that was known. But what is its entanglement entropy? Well, there's a calculation without too much work that gives you another logarithmic divergence, but there's no central charge here. It's not a conformally invariant theory. It happens that there's a reduction by natural log of 2 related to the clean Heisenberg case. So, and there are a lot of generalizations of that since then, but I'm just going to sketch the original simplest case. And here, I'm hoping that to maybe popularize this method, because actually some of what we do now for much more complicated random systems, we still use this technique because it's, at least in 1D, you can really do some non-perturbative things in a fairly simple way. So the idea of this real space functional renormalization group for the distribution of couplings is a nice way to illustrate what renormalization group is. So we look for the highest energy scale and try to treat that. That's like looking in my random chain for the strongest coupling. So I find the strongest coupling, and I want to make some approximate description of what this does that will work ultimately for the low energy physics. And to do that, well, if this coupling J2 were infinitely strong, remember this is a Heisenberg antiferromagnet, it would form a singlet, and those two spins would kind of drop out of the problem, and I would cut the chain. If instead this coupling is larger than the others, but not infinitely large, then it does lock those two into a singlet, but second-order perturbation theory through the excited state of the singlet gives me an effective coupling. So basically J1, J2, and J3 all disappeared. I created a new coupling, and that new coupling has strength that you can guess from perturbation theory. The idea is, if I'm doing perturbation theory between the singlet and the triplet here, that's an energy difference of J2. That's my energy denominator in perturbation theory. And clearly, I wouldn't have any coupling between this spin and this spin. If J1 were equal to 0 or J3 were equal to 0, they wouldn't couple. So it makes sense to have one power of J1 and one power of J3. So what this process does, this says, I look at my infinite chain, and I keep decimating out the largest coupling, and my distribution of couplings shuffles down to lower energy. And the belief, worked out by these people, Chandrasekhar here in Bangalore, was that you wind up with a certain universal distribution of couplings. So it is a attractive critical point in that sense. Whatever distribution I start with, unless it's totally fine-tuned, like all coefficients equal, I will wind up at some universal random quantum critical point. And then the entanglement entropy comes down to some calculation that I will not tell you too much about because it's solving a bunch of slightly painful equations, but you can calculate what is the entanglement entropy of this problem basically by making these sort of rainbow diagrams and figuring out how many of these lines, how many of these singlets, either short range or long range, because I keep forming singlets in kind of a hierarchical way, I just need to count how many of those singlets cross the boundary. So I do that, and I get an answer, which is that log 2. And the nice thing is that it works. So you can do it for the random XX chain efficiently, because that's free fermions. And the upper line is the clean case, and the lower line is the disordered case. And this slope is log 2 times that slope. So this was nice because it was actually not that easy to find a really good numerical test of how good the RSRG criticality was. But it seems to be pretty good. As you go to, because it's free fermions, you can go up to 2,000 sites or 2,000 XX spins. And all the signs are that that log 2 is the exact result. So this would be free fermions C equal to 1 standard conformal field theory. This is the Z equal to infinity random quantum critical point, some kind of effective central charge of log 2, but there's no, as I think we're all pretty sure that there's no algebraic meaning of that log 2. It's just the universal entanglement entropy. Yeah.
Is there anything like a Ramanujan C theorem for these?
No, we had hoped so. So the C theorem is this very universal idea that in conformal field theories you can prove that RG does what you would think, and you kind of integrate degrees of freedom out. So if C is a measure of gapless degrees of freedom, then C decreases under RG. The coefficient of entanglement entropy does not have to increase under RG in general. So we didn't know that. It was pointed out, the example to show that it could go up was by Raul Santa Chiara around maybe a year or two after all this. So that's my examples of ground states. I now want to come to maybe what I said in my original title, which is something about how entanglement is useful for dynamics in various ways. So now we're moving ahead a few years from the early days of entanglement entropy. And I wanted to give what to me is maybe the fundamental meaning of entanglement entropy, and how it ties into this numerical method that has appeared in the background of many things I've showed, but I've never really explained. And I'm still not going to explain what density matrix renormalization group really does, but I will explain what a matrix product state is, because I find that a very concrete way to understand why entanglement matters and why, we talk about entanglement as a resource for this and that. It's pretty easy to understand why more entanglement means that a state requires more effort on a classical computer. And it turns out that the genius of matrix product states, in a sense, is that they let you keep just enough entanglement without making the calculation prohibitive. So to explain what I mean, so this is kind of the hazy idea. Entanglement entropy is related to how much classical information is required to describe a quantum state. So as a simple example, let's take an unentangled state. Suppose I had a product state of n spins. So, spin on site, my basis states here would be like up, down, down, up, or something on my 4 spins. And a product state means that I've got some state vector on S1, some state vector on S2, some state vector on S3, and so on. If I wanted translation invariant, maybe these are all the same. But if I ask, even if I don't let them all be the same, if I ask how many numbers did I require, it would take me, say, 2 numbers for site 1, plus 2 numbers for site 2, and so on. Basically, to make the product state, it only takes a linear amount of information in the system size. But we know that the way many-body quantum mechanics works is that we need an exponential amount of information. So product states are just some tiny corner of all the states in the universe. And what we'd like to find is a method to manipulate or represent moderately entangled states. So what I mean by that is, we just said that ground states tend to have area law entanglement. So they're not product states, but they don't have as much as volume law. If you had a method that worked for volume law, then that's almost like overkill for most of the problems we run into. So if you want DMRG as a method that works well for states that are either area law or maybe area law with log corrections, it's able to keep track and get accurate results on moderately entangled states. And I want to try to make a theory of that, basically, in the next few slides. So what a matrix product state is, and the DMRG algorithm, just to give some history, was invented by Stephen White of UC Irvine. And a few years after, Ostland and Romer gave a picture for what kind of state is DMRG making. It's basic, and now, tensor networks, DMRG, matrix product states, these words are all related, more or less the same thing in 1D. So Ostland and Romer gave a picture of that DMRG is effectively a variational method constructing a certain kind of state that keeps local entanglement but throws away long-range entanglement. And a matrix product state is just, say for 4 spins, I now have upper indices that are not directly physical. They just let me stuff in more information. And these run from, say, 1 up to some bond dimension, we call it chi. When you hear tensor network, well, that all started with, here's a representation of that matrix product state, where these upper indices, you'll note that they appear, each of them, in 2 of the tensors. So they're like bonds, that's why we call it bond dimension. And then there are these legs, which are the connection to physical variables. So we now want to kind of say, why is this still getting to be an even better technique as time goes by? There have been a few ideas over the years since '92 that have really turned this into the kind of powerful technique where we can use it to check a lot of interesting physics, not just in 1D, but in 2D. In fact, that little interlude I have about spin liquids was partly empowered on the theory side by 2-dimensional time-dependent DMRG. So it was originally powerful for ground states in 1 dimension with a gap. But we've now understood a few nice things. One is, sometimes rather than working with a finite system, another nice thing about matrix product states is you can impose translation invariance and say require that all the A's are equal, or maybe you require that they alternate if you want a unit cell 2. And that's kind of a deep statement because we know that with normal quantum wave functions, there's not always a way to generalize them in a translation invariant way to a larger system. If I gave you the singlet, there's no way to directly generalize the singlet to 10 spins or something. But if I give you a matrix product state A, or a matrix, I can just make more copies of it, and I'm guaranteed to get something. It may not be a very good state, but I'm guaranteed to get something that exists for the large system. And that means in practice, we do often what's called infinite system DMRG, or ITEBD. That's the term that Vidal used for time-evolving block decimation. Even with just a laptop, you can do very powerful calculations using this method. So that's this idea that instead of studying a large finite system, we kind of go directly to the thermodynamic limit by imposing translation invariance. If you're asking, well, that sounds like too good to be true, where's the approximation? We still have a finite upper bond dimension, and we'll talk in a moment about how convergence works with that bond dimension. We've learned tricks for gapless systems, we've learned tricks for dynamical properties, we've learned tricks for finite temperature, So the method has come a long way. Let me focus on how this works for criticality, because that's a case where, again, this same Holgi and Wilczek and others formula winds up being quite useful. So this is from that Vidal 2007 paper. And when I have students who are interested in learning this technique, this is the place to start, because with not very much work, you can program this calculation. This is the transverse field Ising model. It has a quantum critical point at j equal to g, which is 0 on this axis. And what this calculation is showing is that your error in using the matrix product state of bond dimension chi. So for example, chi equal to 12 means basically just 12 by 12 matrices. This is hardly overpowering your computer. This is an easy calculation to do in MATLAB or something like that. You find that your errors are getting extraordinarily small once you're 5% or so away from the critical point. That's 10 to the minus 10 with 12 by 12 matrices. But at the critical point, the errors are larger, and you can see that in a sense the convergence is almost exponential down here, but here it's only sort of power law. It's a lot slower at the critical point. And that's another sign of criticality, that the basic idea is going to be that the matrix product state can only capture a certain amount of entanglement related to chi, and at the critical state, there's a diverging entanglement, and that makes it harder, but not impossible. So that led to the idea of finite entanglement scaling. So I want to say a little bit about what that is quickly. You've probably heard about finite size scaling, everyone who's worked on critical phenomena, where you could say criticality is a property of the thermodynamic limit, but there's a systematic way that finite size of the system affects it. Here, if we go to finite bond dimension, that was kind of observed numerically to act like finite size scaling. Basically here, my notation is that chi is the dimension of the matrices, and the effective correlation length I generate, I get pushed off criticality by some power of the bond dimension. And trying to figure out that finite entanglement scaling, they didn't have any observation on what kappa could be, so that's where we found that quite an interesting puzzle. And it's not as simple as finite size scaling, where kappa just winds up being related to nu, the correlation length exponent. So what determines this finite entanglement scaling? And in some ways it's similar, but in some ways it's different to the famous finite size scaling of CFT. There's a nice review by these people. So, and now it comes down to, what did I mean when I said that it was nice to look at entanglement from the point of view of matrix product states? So one of the ways that you learn about entanglement is the Schmidt decomposition of a quantum state. So I'll quickly take you through that, but then sort of illustrate how that relates with some pictures to what happens in the matrix product state. So Schmidt decomposition is the idea that if you gave me a bipartite state, we know that in quantum mechanics, not every state is a product, but the product states do form a basis, which means I can expand any pure state over some basis for A and some basis for B, and then by unitary transformations on the A basis and the B basis, I am led to make these coefficients, instead of a matrix, I can get just non-negative numbers, non-negative real numbers, in front of that. And then a product state, one of these is 1 and all the others are 0. But more interesting cases, there will be some distribution of these lambdas. And then the entanglement entropy is simply expressed in terms of these lambdas. It's just minus lambda squared log lambda squared sum. So what matrix product states are basically doing is an efficient way to kind of keep the largest Schmidt eigenvalues. How many you can keep depends on the bond dimension. So it's like a form of image compression, and that's sort of literal. And I'll draw pictures, or Frank Pullman drew pictures, and I will show them, of an efficient way to kind of compress quantum states that the matrices studied are finite, even if my original state was sort of infinite. And that has led to this whole basis of methods. So that singular value decomposition is actually a simplest way to imagine image compressing a grayscale image, because a grayscale image, if you think about it, is just like a matrix of numbers where the number is the color at each x and y point. So think of this as a matrix where I've got, indices I and j, and the matrix entry is the color, or the depth of gray, I should say. And as you increase the number of vectors you keep in the singular value decomposition, you can see that your image compression, or the accuracy of your compressed image, gets better and better. So you can't see very much there. Here you can see it's a bridge. By the time you keep, say, 256, it starts to look like the Golden Gate Bridge in black and white. So we're doing that with quantum states, and there's something very universal that happens if the quantum state was a quantum critical state with conformal invariance. And there, a different way, a sort of, different derivation almost of the logarithmic formula for CFT critical entropy is to try to figure out what is the distribution of eigenvalues that corresponds to it, that will give you this, C over, in this case, well, the entropy would be C over 6 log psi, the psi being the correlation length. So it kind of, everything diverges when psi goes to infinity, but at some large finite psi, there's some fairly complicated distribution by Calabrese and Lefebvre for what is the distribution of Schmidt eigenvalues. So that lets you develop a theory for this critical exponent kappa. And I won't go into the details of how that's derived, and there are now several different derivations out there in the literature. But this is work with Subrata Mukherjee. I was very proud to be introduced by him. And Frank Pullman, Ari Turner. And the basic result is actually a little bit like what happens in that logarithmic entropy. So if you want, in what Masaki explained this morning, maybe the key surprise is that you start off with a scaling dimension, and yet the scaling dimension of these twist or boundary changing operators is not related to what we normally think of as a scaling dimension, it's related to central charge. So something similar happens here, where the finite entanglement scaling is governed by the central charge, but in an odd way that involves a square root. But this is tested in various places, and I don't know that it's going to be exactly right, but I don't think there could be any exact formula other than this. It works sufficiently well. So that means that in practice, we can converge with a certain exponent, and as central charge goes up, it gets harder to converge, but at least we understand, how to do critical theories, and that lets us understand when we go to 2D critical theories using cylinder DMRG, what is the size of our errors, basically. So that concludes the sort of how is entanglement related to information piece. What I want to talk about now is something about where entanglement teaches you how to differentiate two kinds of localized phase that, at least at the time when this was going on, we didn't really understand how to differentiate so well. So the basic idea, if I took the spin chain that I started with, that I'm using as an example a lot in these lectures, and I added a random z-directed magnetic field, then there's at least, I don't think it's proven to be localized for infinite time, but it is localized certainly if I get rid of the interaction term, the JZ term. That's an example of Anderson localization by the random Z field. So the harder part, and that's this idea of many-body localization, is to understand, is there still any localization when I have interactions? When I call this interactions, what I'm referring to is this would become free fermions through the Jordan-Wigner transformation. This would become an interaction between the fermions. So the challenge that people still, I think, have not totally nailed down, but there's at least a lot of evidence that for any observable time, you can see a localized phase. I can get, a localized phase when the disorder is extremely strong. I can get an extended phase when it's not, and maybe in between there's some kind of phase transition. So that transition, just to kind of update people, there's a lot of work on many different signatures of going from a localized and non-thermalizing phase to an extended and thermalizing phase. And I'm not giving a whole talk on MBL, so I'll talk about those, but I did try to make a list of at least some of them. But the entanglement, I think, in various ways, I'm going to talk about entanglement dynamics, but there's also things like variance of the entanglement and so on. Entanglement has turned out to be a great lens for understanding many-body localization and other kinds of non-thermalization. Because basically, thermal states give you volume law, for the reason I said earlier. If you see something other than volume law, then that's a clue that something else is going on. So the idea of what want to build up to, I guess, let me say a little bit about MBL before I get to our specific calculation, and why MBL is a kind of integrability, but it's different from the integrability that was the hero of the last talk, or that was at least apparent a lot in the last talk. So there's a famous difference in the statistics of energy levels between integrable and non-integrable systems. In non-integrable systems, there's something called level repulsion. Basically, I'm unlikely to find two levels at exactly the same energy or extremely close energies. And Wigner and Dyson explained a lot of that. But if I have a system that is integrable and large enough, then I expect the energy statistics, the energy levels are basically independent, which corresponds to Poisson statistics. And that happens both in integrable models in the sense of like Yang-Baxter integrability, but also in MBL. In MBL, the way to think of MBL integrability is that I've got some orbitals, and each orbital could be occupied or empty, and those are my conservation laws. Or you could, L bits, they're different terms that people use, but if I wanted to make it like localization of electrons, it's just the occupancy of different localized states. So in other words, they are very local conservation laws, while in a Yang-Baxter system, the integrable quantities, the conserved quantities are like sums of local objects. Anyway, so that means effectively that Wigner-Dyson is a property of thermalizing non-integrable systems, but all the other cases tend to give Poisson, and that's something you can look for. And I wanted to say a bit about that, going back to actually uniform spin chains, because I think it will clarify maybe one or two questions about Luttinger liquids I got after the last lecture. But maybe the key way that MBL systems, their integrability is even more magical is we tend to believe that Yang-Baxter integrability disappears under small perturbations, and a lot of work goes into understanding the scaling of those perturbations. But MBL integrability should be stable to perturbations. And yeah, that's one thing that you can look for. So here, this is actually about how the Luttinger liquid behaves under an integrability breaking but not random perturbation. So for this next two slides, let me show what I meant about dangerous irrelevant operators affecting transport in the Luttinger liquid in an example where it's relatively easy to do calculations. So this is my favorite model of what I call a generic Luttinger liquid. You can add this term, it breaks integrability. Sometimes it opens up a gap, but if you're at the right value, the right window of delta, there is a window where this is a gapless Luttinger liquid, even with that perturbation. And you can actually follow, by looking at correlation functions, you can follow the RG trajectory where this is irrelevant, which means that it kind of scales to zero. At long distances, there's some Luttinger liquid point that a non-zero value of this, or this set of non-zero values would scale onto, where this is H, and this is that delta parameter. So you can look and tell that you've broken integrability by looking at the level statistics from exact diagonalization of this Hamiltonian. And Wigner-Dyson and Poisson, the easiest way to understand why they're different, Poisson doesn't have any dip at the origin. It just starts large and falls down. But Wigner-Dyson level repulsion, as I said, means that I'm unlikely to have two levels right next to each other. So this is what level repulsion looks like. This is Wigner-Dyson statistics. Horizontal axis is energy difference, and vertical axis is number of levels in a histogram. Basically, turning up this crosses over the system from Poisson to Wigner-Dyson. So anyway, the argument for why you get Poisson statistics in integral models very quickly, if I've got some big spectrum with 1 billion levels, any two nearby levels are likely to have different values of some conservation law, some conserved quantity, and that means that they don't mix with each other. So the usual Wigner-Dyson argument about mixing and small denominators blowing up the splitting doesn't work for integrable models. Yeah.
Here, I guess the spectrum is the entire spectrum. If you were to focus on an energy window which was very close to the ground state, and then if you look at the level spacing distribution, would it at all, is there any chance that it might? Well,
I think it would look effectively integral. In fact, it would look like a CFT energy spectrum. I mean, you see the ground state, and then you'd see the linearly dispersing boson. So basically, in the low-lying spectrum, you would think that it's integrable. But that would not be the right story at long enough times. I mean, yeah, and it is in a sense, for some quantities, that is the right description. Like if you looked at free energy, which is just going to be some sum over the energy levels, then that would work. But if you look at transport, at any non-zero temperature, it doesn't work. And in fact, that's my next slide. This is proving that the Luttinger liquid in the real world has very odd transport properties. So this is a little bit different from the standard power laws you've heard about in a Luttinger liquid, which is that if you tunnel an electron in or something, you get IV curves or other things that are continuously variable power laws. Here, this is just current correlators to calculate the charge conductivity in the Luttinger liquid. At low temperature, the conductivity of a Luttinger liquid blows up. And that's because, more rapidly than in a normal metal. And that's because the irrelevant perturbations that give me the scattering are scaling to zero. So for example, for these particular values, the Luttinger parameter and so on, you can see good agreement between numerics and the theoretically predicted power law that sigma is blowing up like temperature to the minus 5/3, basically. And yeah, this is, I think, sometimes underappreciated that even like any one-dimensional quantum wire, people hear, oh, one-dimensional quantum wire is a Luttinger liquid, therefore it's a free boson. That works for many things, but I don't think it ever works for transport in the real world. So coming back to MBL, I think a way to define it and explain its lack of thermalization is what I mentioned a moment ago, that it has a complete set of conservation laws that are genuinely local. They're not sums of local quantities, they're just local quantities. Imbri used that to make something that maybe is not accepted as a proof in the mathematical community, but was steps toward a proof of MBL. And recently, that proof has been expanded and maybe refined and maybe made even more rigorous by a group in Belgium. So let me just set up a thought experiment that will tell us that MBL is not the same as Anderson localization, but also not the same as thermalization. And that thought experiment is start with an arbitrary product state, which just means local SZ eigenstate like up, down, up, or something like that, and evolve it under this Hamiltonian that is believed to be in the many-body localized phase. So if I had an extended phase, then Calabrese and Carty taught us that entanglement will grow linearly with time. The other easy limit is that if I've got a sort of one particle localized phase, like Anderson localization with no interactions, J is equal to 0, then my eigenstates are Slater determinants of localized states. And if I let that system go, particles will move some finite distance, they'll move a localization length, and then they'll stop. And that means I would expect that the entanglement saturates at some finite value. And what happens if we add interactions to the localized phase? And in fact, in a way, this calculation works because the entanglement doesn't grow too much, and that's all in this paper. You see something funny happen the moment you turn on interactions. And that is, there's some initial period that doesn't care very much about the weak interaction, but then with no interactions, the entanglement versus time just kind of stops growing. That is the independent particles hitting the localization length. But the moment you have interactions, maybe the surprise to us at the time, the moment you have interactions, you get a growth of entanglement that doesn't seem to stop. And when that growth starts, it might take a long time if the interaction is very weak. But once it starts, the slope is not changing by very much. And note that this is a log linear scale. So this is basically entanglement growing like log t, but in a way where the slope with the log t doesn't care about the strength of the interaction. And that is, anyway, yeah, if I look at transport, you could say, well, maybe this is just delocalizing. But if I look at whether particles are actually moving rather than entanglement, and this is a good numerical proof, or one example of a statement that I made earlier, which is that there are many systems where even if particles are not moving rapidly or not moving at all, entanglement still moves. Here, particles don't move. You can look at the conservation, the transport of the conserved particle number, and it basically gets stuck. So you could say that if you waited infinite time, maybe the particles get unstuck. But at least over some very large observable time scale, and consistent with experiments, things don't come unstuck. And there is a picture of why that works, and maybe I won't get too directly into this, but the picture of how entanglement grows in an MBL state that is hard to prove, but I think makes a lot of sense and it passes numerical tests, is that if I have these localized two-level systems, my sort of conserved states, and if they're far apart, I would expect the effective interaction between them from the interaction term to fall off as some exponential. And then if I'm justified in treating all those pairs independently, then this pair will become entangled at a time, that I guess the number of pairs that have become entangled by time t, I should put it that way, then scales as some correlation length times a log of the bare interaction times time. And that's where, note that the bare interaction, I can break up the log into log j naught plus log t. That means that the slope is only dependent on the localization length of the original problem. It doesn't care about the interaction strength. And that's the part that made me think that this is probably the right picture. So this kind of simple picture of decoupled two-level systems has to break down as we get close to the transition to delocalization. But I don't know of any better picture in the last few years. So I think now, I want to start to connect to the experimental world and talk about things just done in the last couple of years. So what I want to build up to in closing, to prove that we're in the age of quantum information, not just theoretically, but experimentally, and not just in quantum computers, but in materials, I'm going to try to argue that some other entanglement quantity known as the quantum Fisher information is very connected to standard condensed matter observables. So in other words, entanglement entropy is not easy to unpack in terms of like two-point correlators or the other stuff that we can normally measure. It's a very profound quantity and it governs all sorts of things, but maybe we should look for other quantities, and I'm going to argue that this QFI, well, I think other people showed this, but we applied it. The quantum Fisher information is a very nice, accessible way to get quantum aspects of states. So that's going to connect us to neutron scattering and things like that. So I think in a moment I'll take my interlude to show you neutron scattering searches for spin liquids or other kinds of experimental searches for spin liquids for 10 minutes, the part that I didn't get to yesterday. But what I'm going to come back to is this quantum Fisher information and as a way to interpret neutron scattering as a measure of entanglement, basically. And just to kind of explain how this is different from entanglement entropy. Entanglement entropy, I needed to know a state and how to partition the system, but I didn't need any particular observable. It was independent of a choice observable. It's really a fact about the state in the Hilbert space. Quantum Fisher information is a little bit like a generalization of susceptibility that measures how sensitive of an observable is to a change in a parameter coupling to that observable. So I have to pick an observable, but the good news is for a pure state, it's quite simple. It reduces to the ordinary susceptibility. For a mixed state, it's more complicated. And how you can measure why this is a natural thing to measure, I will come back to. So let me quickly switch over to neutrons and spin liquids. All right, so I think this is about where I wrapped up last time, which is there's a new family of triangular lattice compounds based on ytterbium diselenides, and they are our best hope yet maybe to get frustrated magnetism leading to a spin liquid. So the current belief, at least in a simple picture of where these ytterbium selenides sit, is that as you do chemistry, you kind of march toward larger secondary couplings. The belief is that the most important coupling here is not the one I argued for in the Hubbard model. It's like a J2, a second neighbor coupling. But I'm mostly going to talk about two kinds of experiments on materials in this ytterbium-containing category. But they're effectively spin half on the triangular lattice, which there aren't that many examples of, and they don't distort as far as we can tell at any accessible temperature. So as an example of how this search hotted up in the last year or two. These are papers on the archive, some reaching different conclusions and so on. I will focus on ytterbium diselenide with sodium stuck in, and on this paper. But basically, magnetic susceptibility turns out to be the big surprise, so that's why I thought now was the logical time for the interlude, because I just talked about how QFI reduces the susceptibility at low temperature. And in particular, neutrons are great, and I'll also talk about neutrons, but neutrons can't get the very low energy scales where things seem to be happening in this material. So what I mean by that is, if you take this material, I'll show you another material that seems to be a Dirac spin liquid or some kind of gapless spin liquid in a second. This material seems to be happily marching along and has a large specific heat and other features consistent with the Dirac spin liquid until there seems to be some kind of instability. Dirac spin liquid means a gapless spin liquid with like Dirac points of the spin-on excitations. And this was a bit of a shock. It seems like below 25 millikelvin, so very difficult accessible regime, some kind of gap is setting in the magnetic susceptibility. And the left side is just trying to prove that these are good crystals and so on. So this is maybe the biggest surprise in that experimental paper. And that means that maybe, since a gap is opening, unfortunately no experiment and no quantum computer within the near future can resolve that low energy scale. So we don't actually know if there's an instability to RVB or a chiral quantum spin liquid, or there's a nice proposal by Johannes Knolle and collaborators that there's a particular kind of valence bond solid, like a crystal of dimers, that might win on the triangular lattice. And none of these at the moment can be detected with the current experiments at 25 millikelvin. Yeah, they're of order 20 Kelvin. So it's not a very strong magnet, but they're well above. This is quite a low energy scale. Yeah. Yeah, and that comes back to like the message. Right now, quantum computers are good at studying problems at the J scale, or maybe the J over 5 scale, but not the J over 100 scale. So the other material I wanted to quickly mention, which does seem to remain gapless, at least as far down as we can measure, and it let me sketch, why do theorists care about this? This is a so-called 1215 version of ytterbium, zinc, gallium, oxygen. If you followed the field closely, you'd know that there was a 1114 compound version of this a few years ago, but it turned out the atoms tended to switch around. There was site switching disorder, and that probably meant a lot of disorder signatures rather than spin liquid signatures. So Sarah Haravafard made a different compound that seems to solve the disorder problem. And if you measure that compound, they talked to us about it because we had done these time-dependent DMRG calculations on the J1, J2 model. This is the calculation, this is the experiment. You can do cuts and all that, but it seems pretty consistent with the J1, J2 model. But again, neutrons, they can kind of diagnose things maybe at somewhat high energies, because this is milli-electron volts, but millikelvin are like micro-electron volts, so we can do thermal measurements at much lower temperature scales. And what makes the case that this is a Dirac spin liquid is that if you subtract the lattice contribution and the nuclear contribution, so the raw data is the black curve, and I agree with you that the black curve is not going to zero linearly as t goes to 0. But if you subtract two pieces that you think you kind of understand, then the remaining specific heat is going to 0 like a Dirac spin liquid is supposed to. So why is that exciting? Well, I mentioned at the beginning when I showed my picture of the standard model, something that has been a holy grail ever since I was in graduate school is that many theories of the cuprates and frustrated magnets and others, there's some kind of emergent gauge field. So that is, for example, with the cuprates, you do a mean field theory. Actually, Ian Affleck, who was appearing in Masaki's talk, was one of the first people to do this. You do a mean field theory of the Hubbard model and you get D-wave superconductivity. Hooray. The field's history would be very different if people had believed them when they said that back in '87 or whatever. It took until about 1993 in an experiment for people to believe them. But when you go beyond mean field theory, you naturally get sort of abelian or non-abelian gauge fields that are not like our photon. There's something generated that lives in the material. It's like a 2 + 1 dimensional photon, which makes it QED3. We've never found direct evidence of that emergent gauge field in strongly correlated electrons, I would say. There's the Chern-Simons gauge field, but that's a different beast. So now, if we really have this U1 Dirac quantum spin liquid, so I didn't talk about it, but in addition to those gapless spin-ons, there's supposed to be a gauge field that binds them, then there ought to be excitations like monopoles of the gauge field and so on that we could look for. And I really like this recent paper by these three people, because they decided, well, if we could do exact diagonalization and look at all the energy levels, can we map them onto different kinds of gauge excitations, like monopole or bilinear fermion or whatever? Experimentally, we can't do exact diagonalization, but the hope would be that someday we'll figure out, what in neutron scattering or transport or some other mechanism is coming not just from the spin-on, but from the gauge field, because that gauge field has been, a ghost or something we haven't yet found after 30 years or so, and maybe we're getting closer to that. Okay, so with that, now that I've talked about susceptibility in neutrons, I'm going to go quickly back to my main slides. If you're wondering why I had to switch, it's because the aspect ratio is different. So put your mind back in 4:3 format. All right, so is entanglement physical? I think it's certainly physical. Is it easy to measure is a harder question, but this QFI quantity, which in general looks like that, which I don't find super illuminating, is that measurable? And this is where there was a very clever paper around 2016 that I don't think was really built on until recently. But just to kind of show you that at least this formula makes sense. So here, I've got a mixed state. Then the QFI is not just the susceptibility. My mixed state has, some lambdas and some states, and when I sum this particular combination of the lambdas and the matrix elements of the particular observable I'm using to define the QFI, then I get the QFI. Just to check, it's not even obvious that this reduces to the susceptibility maybe, but that's a pretty quick calculation. For a pure state, one of these lambdas is 1 and all the others are 0. And that means these are the terms. Basically, I get the sum over all the ones other than the first of that, and by using a resolution of the identity, I can relate that to the variance, and that's what I said it was in the pure case. All right, so now come the two pieces of magic. The word magic has been used a couple times in the meeting. I don't know why this has to be true, but it is, and it's in this paper by Hauke et al. This is the one I mentioned from 2016. The text I'm showing is from our paper, and I should have said the hero of the work I'm going to talk about is Varun Menon. He is not here, but I understand that his housemate is, so that's something. He's currently a grad student at Harvard, but he did this when he was an undergrad at Berkeley. All right. So the first piece of magic is this quantum Fisher information can be expressed as an integral with some kernel over the imaginary part of the dynamical response function, the same thing that appears in the Kubo formula. And this, we know how to relate this to observable quantities through things like fluctuation dissipation theorems and so on. So that says, if I could measure at all frequencies, which admittedly is not easy in principle, then by integrating over frequency, I could get the QFI. So this is going to be related to the dynamical susceptibility, which is what in turn gets related to neutrons, say. So it's a little bit like Kramer's Kronig in the sense that you never measure all frequencies, but you try to measure the interesting frequencies and then do some kind of logical extrapolation, say, for ultra-high frequencies. The second bit of magic, or at least a use of QFI, is that if the quantum Fisher information winds up being larger than a certain value, then you can actually make an observable independent statement. So I said entanglement entropy doesn't care about the particular observable, QFI does. But if the QFI is larger than a certain amount in an n-particle system, then the state cannot be factorized into small pieces. And that's kind of saying if this thing is larger than k, then the state is at least k plus 1 partite entangled. So that just means, it could be like Schrodinger cat entanglement, like all up and all down. It doesn't mean it has to be a very complicated kind of entanglement, but at least it indicates that you don't have just local independent bits. You can prove not just that you're going beyond a product state, but kind of quantitatively how far you're going. And I'll talk about one application of this, and then I will try to have a bit of discussion. So what that means that, with a little bit of math, you can transform that into an integral over what gets measured in neutron scattering, say. So the observable, I'm going to pick the magnetic moment at some wave vector q. Q equal to pi is the logical one to use in antiferromagnets. So then I can relate the QFI for that observable to this integral where now I'm going to the structure factor, and this is, maybe not the most obvious functional form, but that says, again, if you can measure the structure factor, like S of Q omega, this is the same quantity, I just suppress Q on both sides. S of Q omega at all omega gives you the QFI. And I think the main neutron scatterer who pointed this out or started, seized on this idea of Hauke et al. Was Alan Tennant at Oak Ridge in Tennessee. And their first paper on this was in 2021. Actually, it's the erratum. They're very honest experimentalists. Berlin pointed out that they had a couple of factors of 2 wrong in their definitions and figures. So they wrote an erratum fixing all the factors of 2. I know bigger mistakes than a factor of 2 that have not been corrected with errata, but what are you going to do? So my last sort of technical slide is to kind of explain how this works. And this is done for, again, potassium copper fluoride. So Heisenberg spin chain, because they had that lying around. The nice thing about that is there is a divergence in the susceptibility at low temperature, and therefore in the QFI. And we spent some analytical effort trying to establish that those are the same divergence. Basically, it diverges like the logarithm of temperature to the 3/2 power. So not something you would likely get coincidentally. And using matrix product state calculations on the left, you can compare to that asymptotic form and see that it's working. So indeed, as you go to low temperature, which is high beta, there's this slow divergence of the QFI in, again, the QFI for the observable, that is the moment at pi. And you can now look at the measurements. And the measurements correspond to something like, well, if you remember, if this is larger than k, you get k plus 1 partite entanglement. There are at least 4 spin entanglement in the material at low enough temperature. So it is going up. I don't think you would call that like clearly proving a divergence or something, but actually it's not too bad if you look at the inset. So as far as where this quantity is useful, I mean, Alan has been using it on all kinds of places, but I think the one case where it's most powerful is a quantum critical point, because those often have a diverging susceptibility, and therefore they have a diverging QFI, and therefore you're kind of establishing multipartite entanglement at different kinds of quantum critical points. And that is a bit of a milestone, because we always thought that entanglement, maybe the atomic physicists or the qubit people could measure it, but it wasn't going to be the easiest thing to measure in solids. And this tells you can measure it in solids with an experimental technique that goes back to the 1940s or so. So I guess we're in the age of quantum information, was the subtitle of our talk, but sometimes that means old wine in new bottles, but old wine can taste pretty good. So to kind of conclude, quantum information, maybe what the talk started with is it gives us new questions to ask and new ways to understand the different quantum states that we loved anyway. But it also gives us new goals. Quantum computing is a big one, quantum sensing, quantum communication. There's kind of the set of goals that came out of the quantum information community, but there's also things like how do you measure or generate entanglement just in our condensed matter systems. So a few questions. Hopefully this is just one of many ways to measure entanglement quantities in materials and so on. And then how does entanglement behave in the complex states created when we go away from materials and into these new systems with an incredible degree of control, like superconducting qubits. So all of a sudden, the world of states we need to think about and the processes that act on those states has gotten much larger in the last few years. So that's kind of exciting. You know, I thought I would say a few words just because if you're a student, it can sometimes seem like so much great physics has been done. Is there a lot left? I think the good news is there's a whole lot left, maybe especially in this new quantum era. So just as an example of something we're working on, a famous kind of qubit used for sensing is the nitrogen vacancy center in diamond, which is used for magnetometry. And there, as one object, it is incredibly quantum coherent. It almost behaves like an atom in vacuum, even though it's embedded in the diamond lattice. So that's a quantum sensing technology that is actually making its way to applications. But if you put a bunch of them together, you might have expected, very quantum dynamics or a spin glass or something, but instead, we worked on modeling a system created by Norman Yao. It seems to be not as quantum as you would expect, and so understanding kind of quantum to diffusive or quantum to classical crossovers in that kind of qubit system, we don't understand. In other words, a simple model works to explain the experiment, but we're now trying to do theory to understand why. I think with that, I won't come back to my emergent goals slide. I will say, I'm very honored to be the Chandrasekhar lecturer. I remember when I first came to India as a first-year graduate student, the community was very gracious. I learned a lot. I love the attitude toward physics in India, that we're all very privileged to live in this beautiful world and have some time to try to understand it. So it's been a great week, and thank you very much.
Joel, for not just this talk, but also the previous two. Are there questions?
Can you just go back to the slide with the inequality where you relate the quantum Fisher information to this one? Sorry. So I'm trying to understand. So what you're trying to say is that regardless of what the operator O is, if the state is at least k plus 1 partite entangled, then the quantum Fisher information divided by n is going to be k.
Not quite. It goes the other way. If the quantum Fisher information is large, then the state must be entangled. You could have an entangled state that has small QFI.
Okay. No, because I was just curious, at the end of the day, the experimental data is measuring the quantum Fisher information for just one particular operator. And on the basis of that, you're concluding that the state is entangled. So, okay, so
but that is the direction in which it's a theorem. Like basically, if you want, this QFI is a kind of quantum sensitivity. And if your system was only independent, local objects, it wouldn't be able to have the right kind of sensitivity. It's, I guess, the hand-waving picture. But as I said, 2 pieces of magic means that I don't know of any very quick derivation of either of these facts. But we do cite the original papers, but they're still kind of deep to me. Maybe in a few years I'll derive them. But here, it's pretty, I guess this one is not hard to derive, but it's more like you do some identities with all these lambdas, and they both come out to be equal. But why? And then the second is a little bit more work.
This equation 1, for example, that you have written, this tan hyperbolic beta omega integral, at least in limits, either in a low omega over t or high omega over t, one should be able to rewrite it in some order by order thing. And then those look like some moments of chi prime, which we know how to compute, for example, at least in thermal systems as a effective ground state, static correlation, some more complicated static correlations. Has anybody tried to look at what?
I don't think so. I mean, I think it's a good idea. Like one thing we did was just try to understand how, if chi went as different powers of omega, what would the asymptotics of this be? But we didn't actually do any calculations of expansions of chi or something. But yeah, I'm hoping that now that there are actually experiments using this formula. So I mean, this Nature Physics paper got some attention, but I think it didn't generate a lot of experiments until more recently. But yeah, I do hope that there will be other applications of this.
Yeah, so and related to this, so what are the other things eventually, let's say, you can hope to extract from this QFI? Like, can you just to say like detect other things that we can do for entanglement entropy, like I don't know, topological order or different kind of scaling.
I don't know. I mean, I know the world it kind of came from, and they have a use for it. I don't actually know that it does anything interesting for topological states or something like that. But where it sort of comes from is an interesting question that maybe we should think about as well as theoretical physicists. It's kind of from like ideas of sensing. So as an example of kind of an open problem out there, suppose I gave you 10 very good qubits, which many groups around the world now have. What is the best sensor you can build with 10 qubits? Right now, most quantum sensors work in kind of an independent ensemble approach, which means that your errors go down like 1 over root n, or if you want, your sensitivity goes up like root n, like central limit theorem. But we know that if we could couple them ideally, then there's a Heisenberg limit of sensing, which would be sensitivity going like n. So how to do that in practice is kind of a big question, but that's where QFI tells you something about the power of your system as a collective sensor. I don't know, I mean, topological states tend to have the property that they're inert to many things. You know, they're supposed to be like pretty insensitive to local observables. So I wonder if there's some theorem about, one could try to show something about, you know, QFI not being large in topological states to local observables would be my guess, but I have not seen anything on that.
There are many types of multipartite entanglement. So what I have in mind is something like even a 3 qubit state, like the difference between a GHZ and a W state. So I'm actually wondering whether in some condensed matter context, these whether entanglement, so far from what I'm seeing, it's like a single quantity, but it's really not. So would there be an impact of this actually richness of multipartite?
Yeah, I mean, multipartite entanglement, it is, as you say, very rich. I mean, even bipartite entanglement, I only talked about pure states because even bipartite, once you go to mixed states, starts to get a little bit more complicated. Yeah, so I think the physical consequences of the different notions of multipartite entanglement are accepted to be interesting. And people, you know, my advisor, Xiaogang Wen, was thinking about that for a while, I remember, but I don't think, I don't yet know of as many, I don't know, big successes for the kind of Hamiltonians I think about yet. But I think, yeah, here, this is just the statement by k plus 1 partite entangled, that just means it's not a product state of k particle objects. Yeah. So it's a fairly simple, you know, definition of k plus 1 partite entanglement. But yeah, there are, you know, the question of how to define, I guess there are many entanglement measures defined for multipartite entanglement, and there's a little bit of work on physical consequences of those, but I suspect there's a lot more to do.
Yeah, so I would like to ask a question around about the part where you talk about the entanglement entropy of the Rorschach-Iverson wave function. So this is, I mean, the Rorschach-Iverson wave function is a particular point of the quantum timer model, right? Where you can write the Hamiltonian as a sum of projectors. So the method that you sketched, can it be applied to any Hamiltonian which is a sum of projectors?
I think it depends on this representation of the wave function, but something like it. Okay, so I guess the specific results are for the case where the wave function is a CFT. But I think the key class of problems, you know, I think that in general, entanglement will be simple for wave functions that have this kind of positive weight representation maybe. So, you know, I know what it does when S is a CFT. You know, there are no minus signs in this. It's kind of stochastic or whatever the modern term is. And that I think is related to the fact that you can get it from projector Hamiltonians. Okay. So yeah, it might be interesting to try imitating, you know, I guess I wouldn't be shocked if something like this kind of stitching appears, but I think, yeah, getting from the stitching to the replica limit will be different for different kinds of theories. But I think it's possible that this boundary condition is a little bit more generic.
Okay, thanks.
Further questions?
Yeah, just a short question about MBL. Could you comment a bit about the recent controversy, which seems to say that there's a sort of finite size effect, and that somehow some people do believe that it does not really exist? And
Yeah, I mean, I know, I think there are a lot of theorems that if it does exist in the long time limit, it's under very, very specific conditions, like one dimension, no sort of SU2 invariance, say. But I guess the last I'd heard was that some of the people who had previously proven that it didn't exist, say with SU2 invariance or in higher dimensions or whatever, are the same ones who now think they have a proof along Imbry's lines, that if you took something like, fermions interacting in 1D with no special symmetry, then it could exist. That's like Wojtek, de Ruyck, and Huveniers, and so on. So I suppose, they're one of the arguments, they had this bubble argument for why MBL couldn't exist in the limit of large time before, but I think they now understand, at least they believe, I have not read their proof myself, but a friend of mine, Chris Lauman, has spent like months going through the first part of the proof. I don't even think the second part of the proof is available yet. It's one of these very long mathematical physics things, but at least, yeah, and as you know, there are experiments that people do that I think are indistinguishable between MBL and just like classical glassiness. So people often claim, to have demonstrated a localized system just because it doesn't evolve in the minute or two that they watch it in the lab. That I don't think is so convincing. But what I do think is true is that at least under those conditions of one-dimensionality and no special symmetry, if it does break down, it has to break down like longer than the age of the universe in some cases or something. That's my understanding of the current thinking, at least.
Questions? I have a short one. So you talked about the RSRG, but we sort of understand why it does not work very well if you follow sort of an upward branch and try to get a state in the middle of the spectrum. Does this mean that there's almost no perturbative approach that will ever get the full physics of MBL correct?
Yeah, so RSRG, I mean, in some cases, I think you can say stuff about the upper spectrum, but it tends to be free theories. It's like this RSRGX and things like that, like XX.
But those are sort of dilute resonances, so that's why I'm asking that.
That's right. No, so if you mean in the interacting case, yeah, I mean, I don't know. One of my Berkeley friends, Ehud Altman, was a leader in those RG approaches, so I don't know if he would be the one to ask if he's given up or still a believer. I don't know. But I think the one thing I can say is with RSRG, it seems like for ground states, it's particularly powerful. For excited states, it only works in certain specialized cases, but we're actually trying to wrap up a paper to slightly extend the family of cases where you can do like excited state dynamics with RSRG, but it still wouldn't really address MBL type questions. I think that's fair to say. Because I mean, maybe a problem is, yeah, to kind of illustrate where the problem comes from, like if you're renormalizing down to the ground state, you're always kind of stepping down in energy. If you're doing higher things, you might go up in energy and then go down, but you might wind up with a state and there's another RG path that kind of led to the same energy window that is not the one you were on, and you have some kind of resonance or interference from that other state. So I think it's hard, and yeah, what happens in the non-interacting case is that you're sort of guaranteed not to mix with the other one, but in the interacting cases you do, and I think that's sort of the root of the problem. I think you can deal with that out to some time scale by doing more complicated variants of the RG, and that's sort of what we've done. But I don't think we would claim that what we've done is sort of asymptotic to all times at a finite energy.
Any more questions? Okay. If not, let's then give a big round of applause to Joel for all the